Now let us see what are the extrusion loads acting when your workpiece is under extrusion metal forming technique. The load in the extrusion is your A naught into sigma naught into ln of A naught upon AF, where A naught is the original area, sigma naught is the flow stress, and AF is the final area after the extrusion. So this equation is used when the uniform deformation is there and there is no friction, right? But in actual your friction is available. So in practical conditions the load will be your K into A naught sigma naught ln A naught upon AF, where K is some constant. It will be given in the question. Now if we say that what are the force required in wire or tube drawing, right, when you are drawing a wire through extrusion process, then the load will be your AF into sigma naught ln A naught upon AF, where AF is the final area. Just remember one thing, in the extrusion formula here we have A naught, but in the wire drawing formula here we have AF, that is the final area after the drawing. Now the drawing stress, the stress induced during the wire drawing will be this formula you have to remember, that is sigma naught into 1 plus B upon B into 1 minus final radius upon original radius raised to the power 2B plus RF upon R naught raised to power 2B into sigma B. We can say that sigma no is the flow stress or yield strength, B is your mu into cot alpha, where alpha is the half die angle. If someone is in the question, if it is given that die angle, then you have to take 1 by 2, because alpha is the half die angle, and RF is the radius at the exit and R naught is the radius at the entry point, and this sigma B is known as back stress, right? So you have to remember this formula, that the stress during the drawing will be sigma D is equal to sigma naught into 1 plus B upon B into 1 minus RF upon R naught raised to power 2B plus RF upon R naught raised to the power 2B into sigma B. Now if we want to find out what is the maximum reduction during one pass, maximum reduction one pass per pass will be if your drawing stress will be equal to your yield strength, that is sigma D will be equal to sigma naught. So sigma naught will be equal to sigma naught into 1 plus B upon B into 1 minus RF upon R naught raised to the power 2B plus RF upon R naught raised to the power 2B into sigma B. This formula is used when your back stress is given in the question. If back stress is not given in the question, just remove this term. That means the maximum reduction per pass will be equal to sigma naught is equal to sigma naught into 1 plus B upon B into 1 minus RF upon R naught raised to the power 2B, right? So, and all the B is your mu cot alpha. So from here you will be able to get what is the maximum reduction per pass. Now let us move towards your sheet metal operation, right? So we have two sheet metal operations. One is your piercing, or you can say punching, and another one is your blanking. Both of them are the shearing process. The holes or in the metal, the material is removed with the help of your shearing forces. So we can say that if let us say this is a workpiece and this is a hole which we get after the piercing. So this is the case. In piercing, when we are talk about the piercing, the leftover after the punching operation, the leftover material is the workpiece. This is a useful thing, and which we removed because of punching is a waste in the piercing or punching. In the punching, with the material after punching is your product, or the material which is removed by the punching is a waste, while in case of blanking, the material which is removed because of punching, this is the workpiece, that circle is a workpiece, and the remaining part, this part is a waste, right? So there is a difference between punching and piercing. Both are the same process, just they are differing about what is the useful product and what is the waste product. So if we say that clearance is that between die and punch there must be some clearance to allow the punch to move. So the die size must be more and punch size will be less. So the distance between them is your clearance. So we can say that in the punching, the punch is the size of the hole which you want, the size of the hole. So you have to remember that in punching, this P is for punch. In punching, punch is the accurate size of the hole, and die, the die is having some clearance. So we can say that the size of the die will be the punch size plus 2 times the clearance, right? Clearance is on the both sides, so it will be 2 times the clearance. While in your blanking, if we talk about blanking, the blanking, in case of blanking, your die will be of size of hole, die will be of the size which of the hole which you want, and punch is having some clearance, so that you can say that punch is having less diameter than the die, so the punch size will be equal to die size minus 2 times clearance, right? So just remember that in punching, punch is the size of the hole. Other thing you will easily remember, just the confusion where you have confusion, that in which process the hole size is the punch size is the size of the hole, or the die size is the size of the hole. So remember that in this P and P you can correlate that in punching, punch is the size of the hole. That means in the blanking, die is the size of the hole. And clearance formula will be your 0.0032 into T. T is the thickness of the sheet, under root tau. Tau is the shear strength of the material. So clearance will be equal to 0.0032 T under root tau, and total clearance between the punch and the die will be equal to 2C. Total clearance will be 2C. If we are saying that what are the force exerted during the punching and blanking, the force will be equal to LT into tau, right? LT into tau. L is the length of the punch, T is the thickness of the sheet, and tau is the shear strength. And if the punching, if you want to do the punching of the holes which are less than the thickness, the diameter of this hole is less than the thickness of the sheet, then the punching force will be, the maximum punching force will be the pi dt sigma. D is your diameter of the hole, sigma is the normal stress or yield stress, divided by d by t raised to the power 1 by 3. This is the maximum force when the hole size is less than the thickness of the sheet. So it will be equal to pi dt sigma upon d by t raised to the power 1 by 3. If we can say that what are the minimum diameter of punching, that what is the minimum diameter you will get in the punching. So the minimum diameter, for the minimum diameter we are saying that the piercing pressure which you are exerting will be equal to the strength of the punch. So the piercing pressure will be area of the shear, that is pi dt into tau, this is the force, equal to the strength of the punch, that is sigma c into pi by 4 d square. So from here you will get this d, this is the minimum diameter of the punching which you will get through this process. Next is we are using that shear on the punch. That shear is giving on the punch, instead of a flat face we are giving the punch some inclined surface, so that because of this shear, the shearing force will reduce, right? If the flat surface is there, then you have to suddenly that shear the area. If this is the shape of the shear, so gradually it will shear the area, so it will reduce the shearing force and it will distribute the cutting action over a period of time. If the shear surface or the punch surface is a flat, then the sudden shearing is take place. But if you apply a shear on the punch, if you make this length some inclined, so it will distribute the shearing over a period of time, so it will be gradually shearing. So because of the shear, remember one thing, because of the shear your maximum force which is required to punch will reduce, but the total work done will be same. The total work done will be same. The energy which is required to shear that hole is same, while you are doing that piercing with the help of your flat or the straight punch, or with the help of a shear punch, that the energy consumption will be same. So the force required because of shear will be, if the shear is there, then force required will be F max, that is LT tau into TP divided by S, where T is the thickness of the sheet, P is the penetration, how much penetration you provide in fraction, and S is the shear on the punch, how much shear you will give the punch. So the force because of this shear on the punch will be F max into TP by S. There is a process known as fine blanking. In the fine blanking, that clearance is very small clearance we are giving to the workpiece or to between the die and the punch. And if the clearance is small, we can say that you will get the close tolerance. You will get the almost the same diameter what you want. So in the fine blanking, if small clearance is there, and so that in that case your pressure pads are used to hold the workpiece so that there should not be any deviation in the diameter. So the small clearance is there in the fine blanking. And if we're talking about what are the punch and die material, so the commonly used punch and die material will be the tool steel. But if you want the maximum production or the high production, then carbides are used to make die and the punch. Right. So this is your shear sheet metal operation. Now the next topic of our discussion is your drawing. So we can say that drawing is the plastic deformation. Drawing is the plastic deformation process in which a flat sheet is formed into the 3D part. There is a flat sheet you have. You just allow a ram to strike on it, and it will take the shape of a cup sized object. So that is your process drawing. So in the drawing, the depth of this cup is very greater than the thickness of the wall, the wall thickness of the cup. So that process is known as drawing. So in the drawing, what we have to take, what is the blank size, that your initial product size, what is the blank size you have to take to make a particular your shape of the cup, that some height, some diameter, some thickness. So we can say that the capital D is the diameter of blank, and capital D is the diameter of blank, small d is the diameter of the cup which you want, and h is the depth, and r is the radius of the corner. That corner radius, suppose we can say, let us say that this is the cup you want to make this kind of a object. So this diameter is small d, this is your height h, and this radius of corner, this corner radius is small r. So we can say that if this small d is greater than the 20r, then the blank dia will be equal to under root of small d square plus 4 into small d into h. This is the blank size. Blank size is your initial size of that workpiece or the sheet. If this diameter small d is between 15r to 20r, then we can take the blank size is equal to under root of small d square plus 4dh minus 0.5r. Right, in that we have to minus 0.5r, and when it is less than 10r, when this diameter of this cup is less than the 10r, so we can say that the blank size will be equal to d minus 2r whole square plus 4d into h minus r plus 2 pi r into d minus 0.7r. Right. If we talk about your GATE question, then you don't remember this third formula. No need to remember this third formula. Very less chance are there that question will ask on this. Just these two formulas you have to remember. If diameter is greater than the 20r, then under root of d square plus 4dh. If it is between 15r to 20r, then it is d square plus 4dh minus 0.5r. Right. We already see that this r is the radius of this corner, capital D is your blank dia, small d is the dia of cup, and h is the cup height. So this is your drawing. And if we can say what is the drawing force, how much force is acting on the blank to make this cup size of diameter small d, then the drawing force will be equal to pi dt into tau into capital D upon small d minus c. C is the clearance. So we can say that this small d is the diameter of this cup, t is the thickness of this cup, and tau is the shear stress or the yielding shear stress. So the drawing force will be pi dt tau into capital D upon small d minus c, where this c is the draw clearance, and this draw clearance will be equal to the punch diameter, that is the punch diameter, or it is equal to die opening dia, the opening dia of the die minus 2.5 t. That is the C. C value is die opening dia minus 2.5 times T. So this is the drawing. If we can say that one process is known as, that is deep drawing. So deep drawing is when the cup height, that is h, is more than half of the diameter. If you can say if h is more than the d by 2, then the drawing process is known as deep drawing. And if we talk about what are the various stresses acting on the deep drawing, then on the flange of the sheet it is biaxial tension and compression, and in the wall of this cup, on the wall of cup, we have uniaxial tension, right? In the flange, both tension and compression, or in the this wall of the cup, we have only uniaxial tension. And the deep drawability, there is a ratio known as deep drawability, that is the limiting drawing ratio after which your hole is pierced. If you increase this limiting, if this ratio, that is capital D by small d, this is the maximum ratio at which you will be able to make this cup, right? If you increase this, then the hole will pierce, just like your blanking and punching, the hole will pierce. So the limiting drawing ratio, that is LDR, will be equal to capital D upon small d. If we talk about what are the various defects in the drawing process, then the first one is your wrinkle. I am not saying anything, just what are the various defects, what are the cause of that defect, only we are discussing that. If wrinkles are there on the wall of the cup, then that is because of insufficient pressure. The pressure exerted by the ram is not sufficient. If there is fracture on the wall, then it means too much pressure is there, pressure exceeding the limit. If there is orange peel, one defect is orange peel, so that is because of the coarse grain structure of the sheet. That sheet is of coarse grain structure, and you have done the annealing at high temperature, right? This is the cause of orange peel. Earring, cause of earring is the anisotropy. Earring means some irregular shape irregular shape is there on the top of the curve, then or top of this cup, this will take this kind of a shape, that is earring. That is because of anisotropy, that the properties are different in different directions. That's why this anisotropy, because of this anisotropy, earring will occur. And another one is the your stretcher or luder, the one kind of defects. That is because you have done the plastic deformation due to inhomogeneous yielding, right? Stretcher and luder is because of plastic deformation due to inhomogeneous yielding. Your yielding is not homogeneous. And another one is the surface scratches. On the surface some scratches are there, then that is because of insufficient lubrication. That scratches on the surface is because of that lubrication is not sufficient. Next process is the powder metallurgy. This is an important topic for your Coal India Limited. Powder metallurgy. In powder metallurgy, your fine powdered metal, right? You convert the metal into fine powdered. They are blended, mixed with lubricants and binders, then compacted. We exert a your pressure on it and make some compact. Then sintered. Then we allow it to heat so that bonds will form and that porosity will decrease in a controlled atmosphere. Controlled atmosphere means there is no oxygen present. So this type of manufacturing process is known as powder metallurgy. Powder metallurgy is the fine powdered metal are first blended, then compacted, then sintering in a controlled atmosphere. That is the powder metallurgy. So how you can make your powder, how you can manufacture the powder? There are various ways to manufacture the powder. First one is atomization using a gas stream. We atomize the liquid metal, and using a gas stream we pass through that molten metal through a gas stream, and it will atomize, and that is used for the low melting temperature material. The material whose melting temperature is less, like zinc, tin, aluminium, lead, these all are used to. For these we can atomize these liquid and make the powder form. Another one is the reduction or electrolytic deposition, or through machining, milling, etc. Number of ways are there to make your metal powder. After making the metal powder, we'll go to the blending. In blending, we can mix this metal powder along with your lubricants and binders. But what lubricants will do? Lubricants will improve the flowability. when you pour the powder in the some specified die or some specified cavity of which shape you want, right? So when you allow that powder to fill that cavity, then this lubricant will help you to increase the flowability of the powder so that it will reach to the all sides, all corners of the cavity, right? So lubricants will improve the flowability, but the major disadvantage of using this lubricant is it reduces the strength. It reduces the strength of your product or workpiece, and generally graphite is used as your lubricant. Then binders are helpful to make the bonds between and it will be acting as a binding agent between the different particles, different powder particles. So it will help in making the bond between the different powders. So generally thermoplastics or water soluble your methyl cellulose is used as a binder. Either you can use the thermoplastics or methyl cellulose. Then after the blending, we'll do the compacting. In compacting, we pressed it into a green compact. We pressed it, and because of this pressing, that powder will take the form of the cavity. But the one major disadvantage is after compacting, still porosity is very high. Right? There are so many pores on so many pores on your powdered product. So in that, after compacting, the density is 70%, right? 30% still your unfilled spaces are there. So to fill this unfilled spaces, we are using the sintering. Or sintering is used after compacting, that we can heat this compacted product up to 0.75 of its melting temperature, right? Under the controlled atmosphere, that is without no oxygen. We heat it so that bonds will form, some hardness will come, some toughness will come, and because of this heating, some diffusion started, recrystallization will be there, that new grains will be there, grain growth takes place because of this heating, and final product will make. And after the sintering, the density of the product is 95%. So we can say that because of the sintering process, your strength is increasing, brittleness of the product is decreasing, porosity is decreasing because 95% is the density, and toughness of the material is increasing. So this is the advantage of sintering process. So by this we can be able to make the product based on your powder metallurgy, right? There are two various process. One is the infiltration. In infiltration, what we do is we dipped this product into a low melting temperature alloy. Right, we have a low melting temperature alloy liquid. We dipped this powdered product into this, and because of some capillarity, this alloy will enter into the pores, and you will get that strength will increase of the product strength will increase and porosity will decrease. So then this process is known as infiltration. Similar kind of process is known as impregnation. In impregnation, the powder metallurgy or powder manufacturing component kept in the oil bath. We kept that product in the oil bath, and oil will fill the cavities or the pores with the help of capillary action, and this oil will act as a lubricant during the service. When you take the service from this product, then it will help in the lubrication. That oil slowly it will come out and it will help in the lubrication. The best example of impregnation is your self-lubricating bearing. Self-lubricating bearing is made up of your powdered metallurgy, and impregnation is done so that when bearing is in the service, that after in the service it require no lubricants, because of this oil it will act as a self-lubricating bearing. So that the name suggests, it is a self-lubricating bearing, no need for extra lubricant here. So this is the powder metallurgy. Now let us discuss the very important topic of your production engineering, that is limits, fits and tolerance. You will definitely get one question in your GATE if you are talking about the GATE exam. So let us discuss what is the limit, fits and tolerance. Some definitions let us see first. What is the basic size? Basic size is that size at which all the limits are applied, that is your lower limit or upper limit. So if we say that there are three parameters in the limits, fit and tolerance, one is the basic size, one is the upper deviation, and another one is the lower deviation. Then this is the deviation to its actual, that basic size, how much we can deviate, because the manufacturing process is not 100%, means that if you want that you need a 100 mm dia, so it is not possible to make 100 mm dia itself. There is some tolerance must be there, that is 100.01 to 99.99. so because of the manufacturing error, some limits fits we have to take care of. So we can say that this is upper limit, is the upper limit. If we can say upper limit is basic size plus upper deviation is the upper limit of the product, and basic size minus lower deviation is the lower limit of the your hole या फिर shaft. So we can say what is the tolerance. So tolerance is your upper limit minus lower limit. This is the tolerance, and this tolerance may be unilateral or bilateral. What do we mean by unilateral or bilateral? If the tolerance is your unilateral, then we can say that both, that is the upper limit and lower limit, will be on same side of the basic size. Suppose if you can say, let us say 100 mm is the basic size, so both upper limit and lower limit will be on the one side, that is, let us say upper limit is 100.05 and lower limit is 100.01. so that is on the same side of 100. If we can say it is a bilateral, that means the upper limit and lower limit are on the either side of the basic size. That means if we can say 100 mm is the diameter, so let us say upper limit is 100.05 and the lower limit is 99.95. so in this case the limits are on the either side of the basic size, so that system is known as bilateral system. So we can say that the upper limit will be the basic size plus upper deviation, and lower limit will be the basic size minus lower deviation. And there is a term called fundamental deviation. So the fundamental deviation is that deviation which is close to the basic size, So it may be upper deviation or lower deviation, it may be of hole or it may be of your shaft, anything it will be. The deviation which is close to the basic size is known as your fundamental deviation. There are three types of fits in the production. One is clearance fit, another one is the tolerance transition fit, and third one is the interference fit. Let us discuss one by one. First of all, let us see what is the clearance fit. This is the hole. We can denote hole like this, right? And let us say this is some datum, some reference level to measure the diameter. Some datum is there. So we can say, suppose this is the hole. This is the upper limit of the this is the upper limit of the shaft. This is the lower limit of the shaft, and this shaded area is the tolerance of the shaft. This is your hole, right? Hole we can represent like this. So this is the upper limit of the hole, this is the lower limit of the hole, and this is the shaded area. So we can say that if the lower limit of the hole, this is the lower limit of the hole, means minimum this diameter you can allowed. If the minimum diameter of hole is greater than the maximum size of shaft, right? One thing you need to understand, the shaft has to insert in the hole, right? We can say if the lower limit of the hole, the minimum size of the hole is greater than the maximum size of shaft, that fit is clearance fit. Because if this is the case, then obviously that the upper limit of hole and lower limit of shaft will be different, right? If the lower limit of the hole, the minimum size of the hole is greater than the maximum size of shaft, then obviously the maximum size of hole is obviously greater than the minimum size of the shaft. That is too obvious. So we can say that if this is the case, that the maximum size of the shaft is, the maximum size of hole, the minimum size of hole is greater than the maximum size of shaft. then it is known as your clearance fit. So we can say what is the minimum clearance? What is the minimum clearance between these hole and shaft? The minimum clearance is the maximum limit of the shaft. This is the maximum limit of the shaft. This is the minimum limit of the hole. So this one is the minimum clearance. This much is the minimum clearance. इतना clearance तो रहेगा ही रहेगा इन दोनों के बीच में, right? इससे कम नहीं हो सकता, right? So the minimum clearance is that the minimum clearance is the upper limit of the hole minus the lower limit of the hole minus upper limit of the shaft is the minimum clearance. And maximum clearance कितना होगा? Maximum clearance is upper limit of the hole minus lower limit of the shaft. This is the maximum clearance, right? Maximum clearance कितना होगा कि अगर होल का साइज सबसे बड़ा हो, शाफ्ट का साइज सबसे छोटा हो, then the difference will be the maximum clearance, that is the upper limit of the hole minus lower limit of the shaft. So this is the case of your clearance fit. Now let us discuss what is the transition fit. Transition fit क्या होता है? Suppose this is a shaft, this is the lower limit, this is the upper limit, right? This is the hole, this is the lower limit, and this is the upper limit. We can say that the lower limit of the hole, this lower limit of the hole is intersecting this tolerance zone of the shaft. Is intersecting this tolerance zone of the shaft. That means that the upper limit of the shaft का जो upper limit है, that is greater than the lower limit of the hole. If this is the case that the upper limit of shaft is greater than the lower limit of the hole, then that fit is known as the transition fit. If your upper limit of the shaft is greater than the lower limit of the hole. So we can say what is the maximum clearance. Maximum clearance, how much you will get? The maximum clearance will be your upper limit of the hole. This is the upper limit of the hole minus lower limit of the shaft. So this is the maximum clearance. And what is the maximum interference? When it will interfere? If maximum interference will be the lower limit of the hole, this is the lower limit of the hole minus the upper limit of the shaft. So this distance is your maximum interference. This much is the maximum interference, and this fit is known as your either force fit, tight fit, or push fit. So this is a transition fit. Next is your interference fit. Interference fit means, suppose this is a shaft, this is the upper limit, lower limit, this is the hole, this is upper limit, lower limit. If the lower limit of the shaft is greater than the upper limit of hole, शाफ्ट का सबसे छोटा साइज भी होल के सबसे बड़े साइज से भी ज्यादा है, then it is known as interference fit. So interference fit का मतलब कि ये शाफ्ट आपका अगर ये होल का सबसे बैक आपका मैक्सिमम साइज भी लेंगे, then also this shaft is not able to go inside the hole. So this is the case when your lower limit of the shaft is greater than the upper limit of the hole, then that fit is known as your interference fit. So in this, what is the maximum interference? The maximum interference is upper limit of the shaft minus lower limit of the hole. This is the maximum interference. And what is the minimum interference? Minimum interference is your minimum limit or lower limit of the shaft minus the upper limit of the hole. This is the maximum interference, minimum interference. So this is the interference fit. So these are the three types of fit: clearance, transition, and interference fit. There is a term known as allowance. The allowance is the minimum clearance on the shaft hole assembly or maximum interference, that is known as allowance. Right? अब कुछ देखेंगे, आप चीजें देखेंगे. होल शाफ्ट असेंबली के जो आप रिप्रेजेंट करते हैं, दिस इज द वे ऑफ रिप्रेजेंटेशन ऑफ होल टॉलरेंस एंड फंडामेंटल डेविएशन. Three terms are there. One is this 100 capital F 8. Another one is 100 small f 8. The capital letter is used for hole and the small letter is used for shaft. ये याद रखना है. Capital is used for hole and small letter is used for shaft. जो ये 100 है, this 100 is the basic size, 100 जो है वो basic size है. जो ये F है, this will give you the fundamental deviation. Fundamental deviation is which is close to the basic size. और जो ये 8 है, it will give you the tolerance zone. Tolerance zone देगा आपको ये 8. Similarly, in the shaft, this 100 is the basic size, F is the fundamental deviation, and 8 is the your tolerance zone. Right? So tolerance will be equal to, formula अगर याद रखेंगे, tolerance will be equal to K into I, some constant, some K is a constant or some parameter, we'll see. I का वैल्यू क्या होता है? This formula you have to remember, I is equal to 0.45 into d raised to power 1 by 3 plus 0.001 into d. Right? D is the diameter, which diameter we'll see. And this I which we calculate from this formula is in micrometer, and in this formula you have to put the diameter in mm. Don't forget this. You have to put the diameter in mm, then you will get the value of I in micrometer. And this D is, ये D क्या होगा? आपको कुछ टॉलरेंस के कुछ डायमीटर रेंज दिया होगा. सपोज इफ वी कैन से दिस इज द बेसिक साइज ऑफ 100, सो दिस 100 के लिए आपको कुछ रेंज दिया होगा क्वेश्चन में, लेट अस से 80 to 120. सो दिस डायमीटर विल बी द अंडर रूट ऑफ दैट बेसिक, दैट रेंज 80 into 120, अंडर रूट ऑफ 80 into 120. And fundamental deviation, this 8 will give you, this 8 will say that which is its fundamental deviation. Suppose if I can say that this is 8, that means it is related to the series IT8. IT is Indian tolerance of level 8, and this is equal to 225I. I आपने यहाँ से कैलकुलेट किया है, यहाँ से आपका आ जाएगा फंडामेंटल डेविएशन. राइट, we'll see how to solve a numerical. एक न्यूमेरिकल सॉल्व करके देखेंगे. एक चीज याद रखेंगे दोस्त, फॉर होल्स की बात कर रहे हैं. फॉर होल्स, if this letter F, if this is from A to H, A B C D E F G H, from A to H, for hole the fundamental deviation is positive. The fundamental deviation is positive means what? The fundamental deviation positive means the lower limit of the hole, the lower limit of the hole is greater than the basic size. So right, fundamental deviation positive means if I draw here that for the hole, what do we mean by that? What is the meaning of fundamental deviation positive? If I draw here, suppose this is the hole, this is the datum line, this is the reference here, basic size. Fundamental deviation means, suppose this is the hole, I represent hole like this. So this is the lower limit of the hole, this is a straight line. This is the lower limit of the hole. So this is the tolerance zone. So I can say this is the limit closest to the size closest to the basic size is the fundamental deviation. So this is the fundamental deviation positive. This means the fundamental deviation positive. Right? So from A to H the fundamental deviation is positive. From H to Z the fundamental deviation is negative. That means this size is the whole, that fundamental deviation means that the closest dimension is less than the basic size. The closest dimension is less than the basic size. And for capital H, if this letter is capital H, for capital H fundamental deviation is 0. So this is the representation of capital H for the whole. Suppose this is the basic size, this is the datum or reference level. So fundamental deviation 0 means the lower limit of the whole is coincide with the basic size, and this is the upper limit of the whole, this is the tolerance zone. By this you can represent the H, capital H for the whole, fundamental deviation 0. Right? So it means that for the whole from A to Z your fundamental deviation is decreasing, at H it is 0 and then decreasing. So that's why this lower limit is coinciding with the basic size. आपके होल में क्या हो रहा है, होल के अंदर आपका फंडामेंटल डेविएशन पॉजिटिव से 0 हो रहा है, 0 से नेगेटिव हो रहा है। सो ए से शुरू हुआ होगा, ए से धीरे ऊपर से शुरू हुआ होगा, ए से अगर हम बात करें लेट अस से इट इज ई, दिस इज ई। सो ऊपर से शुरू होते होते जब आप आए एच के ऊपर, जब आप एच पे आएंगे देन दिस इज द ओनली द दिस वन इज द बेसिक साइज, दिस वन इज द बेसिक साइज एच के ऊपर। तो इसीलिए आप अगर होल की बात करें फॉर फंडामेंटल डेविएशन 0, सो दिस इज द रिप्रेजेंटेशन। शाफ्ट के केस में ये उल्टा हो जाता है। इन द केस ऑफ शाफ्ट फॉर स्मॉल a टू स्मॉल h द फंडामेंटल डेविएशन इज नेगेटिव। The fundamental deviation is negative means for the shaft, if let us say this is the basic size, this is the reference level, the fundamental deviation is negative means this kind of shaft, this kind of shaft. This is the fundamental deviation. This is the fundamental deviation. This is the fundamental deviation. Negative means the closest dimension will be your negative, less than the basic size. So for A to H, this is negative. At small h, it is 0, and at from H to Z, it is positive. Right. So in holes, the fundamental deviation. Suppose this is the fundamental deviation line. So for the holes, the fundamental deviation is first positive, then 0, then it is decreasing in this direction. For the shaft, it is first negative, then 0, then it is increasing for the shaft. Right. So if we can say, if we want to represent the small h for the shaft, so this is the representation of small h, क्योंकि यहाँ से आप नेगेटिव से शुरू होकर पॉजिटिव की तरफ जा रहे हैं तो बीच में h आएगा, सो दिस इज द रिप्रेजेंटेशन ऑफ h. इन दिस केस द अपर लिमिट ऑफ शाफ्ट इज क्लोजिंग टू द बेसिक साइज. इस केस में अपर लिमिट शाफ्ट का बेसिक साइज को क्लोज करेगा, बेसिक साइज को कोइंसाइड करेगा इन स्मॉल h. इन कैपिटल H में लोअर लिमिट ऑफ द शाफ्ट विल कोइंसाइड विद द बेसिक साइज. ये याद रखना है, ये कॉन्सेप्ट है ताकि आप क्वेश्चन सॉल्व कर सको. नाउ लेट अस मूव टुवर्ड्स अ क्वेश्चन. लेट अस से दिस इज अ क्वेश्चन फॉर अस. The diameter is 100. For hole, this is capital F 8. For shaft, this is small h 10. So basic size is 100 mm. Diameter range is 80 to 120. So capital D will be 97.98 mm. And I will be on this basis from this formula 0.45 d raised to power 1 by 3 plus 0.001 d. From this I will be approx 2.17 micrometer. Right? This is the I. For IT8, if we can say for hole, this is for hole. For hole, IT8 is 25I. This value will be given in the question. कि ये 25 होगा, 64 होगा, क्या होगा? This will be given in the question. So the IT8 will be your 25I. So this will be 25 into 2.17. This will be 54 micrometer. And for shaft, this is IT10. And IT10 will be equal to 64I. So this will be 139 micrometer for shaft. For shaft. Right. If we can say that for the shaft, this is H. So the fundamental deviation of the shaft is 0. Right. Fundamental deviation of the shaft is 0. And the fundamental deviation of the hole. This formula will be given in the question. What is the fundamental deviation formula for corresponding to 8, F8? So it will be given in the question. So the fundamental deviation of the whole formula will be 5.5 into d raised to power 0.41. D का value रख देंगे to here 97.98. Then you will get the fundamental deviation of the whole will be 36 micrometer. 36 micrometer. Now let us see. There is a letter F. F comes between A to H, capital A to capital H. That means the fundamental deviation of the whole is positive. If the fundamental deviation of the whole is positive, so we can say we will get the lower limit of the whole is greater than the basic size. So what is the lower limit of the whole? Because fundamental deviation is positive, so the lower limit will be closest to the basic size, and the lower limit will be equal to your basic size plus fundamental deviation. Right? In this case, which we studied earlier, let us say this is the case, this is the basic size and this is the fundamental deviation. So lower limit of the whole will be basic size plus fundamental deviation. This is F, let us say. Right? So the basic size will be basic 100, fundamental deviation for whole is 36 micrometer. So this is 0.036. So 100.036 is the lower limit of the shaft or hole. What is the upper limit? ये क्या होगा अपर लिमिट कितना होगा, दिस वन इज बेसिक साइज प्लस फंडामेंटल डेविएशन प्लस टॉलरेंस, राइट, बेसिक साइज प्लस फंडामेंटल डेविएशन प्लस tolerance. So tolerance will be for the tolerance will be your, where it is your 54 micrometer, right? You will calculate, this will be 0.054 mm. So tolerance will be 0.054 mm. So basic size will be 100, fundamental deviation for hole will be 0.036, this will be 0.054, so this will be equal to 0.09. Right, this will be 100.09. The upper limit of the hole will be 100.09. If I represent the hole here, this is 100 mm, this is the lower limit 100.036, this is the upper limit 100.09. Comes to the shaft. The fundamental deviation of the shaft will be 0 because it is small h for small h, it is 0. So that means if the fundamental deviation is 0 for the shaft, suppose this is the shaft and this is the fundamental deviation 0, that means the upper limit of the shaft will be equal to basic size. The upper limit of the shaft, in this case the upper limit of the shaft will be equal to basic size. So this will be the upper limit of the shaft, that is 100 mm. What is the lower limit? The lower limit will be, ये कितना होगा lower limit? Basic size minus tolerance. Basic size minus tolerance. So this will be your basic size minus tolerance, and tolerance for shaft. Now comes to shaft. Shaft is IT 10. For 10 it is 0.139. So this will be your 100 minus 0.139. It will come 99.861. So this will be 99.861. देखने से पता लग रहा है which this is of which kind of fit? Clearance fit. Why? The upper limit of shaft is lower than the lower limit of the hole. Clearance fit. Minimum clearance कितना होगा? 100.036 minus 99. Minus 100. This is 100. Right? This is the minimum clearance. This is the minimum clearance. Maximum clearance कितना होगा? 100.09 minus 99.861. This is the maximum clearance. ऐसे कोई भी आप क्वेश्चन सॉल्व कर सकते हो, राइट? जस्ट थोड़े बेसिक्स क्लियर होने चाहिए, देन इट विल बी इजी टू सॉल्व द न्यूमेरिकल ऑन लिमिट, फिट्स एंड टॉलरेंस. Our next topic of discussion is the casting process. Right, let us discuss what is the sand casting. In the sand casting, we are using the sand as a mold material. What we are doing in the casting process, first of all, we make a pattern. एक pattern बनाते हैं of that shape of which you, आपको जैसा shape चाहिए उस shape का एक pattern बनाते हैं. That pattern may be of wax, may be of your wood, or maybe of anything. So on that pattern we pour a sand, or this in the sand casting we pour a sand and make a mold, right? After making the mold, we remove the pattern and we pour the molten metal into that mold cavity, and after the complete filling of the mold cavity we allow it to solidify, and after the solidification we remove we just remove that solid metal from the mold cavity, and we just cut the unnecessary things and finish it, and the casting product is ready. So in this case, let us say that suppose this is a casting cavity, this is a mold cavity, and from here the molten metal is coming. So this is this funnel shaped object is known as your pouring basin, and this is known as sprue, which is a tapered, right? And this horizontal is your runner, and the entry into the mold cavity is through gate, which is known as in gate. The upper part of the mold cavity is known as cob, and the lower part of the mold cavity is known as drag, and this extra point or this mold is known as riser. Each and every component of this casting has its own significance, right? We will discuss it. So the molten material is coming with in the effect of gravity. Because of gravity force, the molten material is coming inside the mold cavity, fill the mold cavity, and we are allowing it to solidify. And after solidification, as in the sand casting, we break the mold and remove the product. So in the sand casting, at each and every time when you want to make a casted product, at each and every time you have to break the mold. So for each product you have to make new mold. So we can say some of the definitions. Let us say, what is a pattern? Pattern is the replica of the final object which you want to be made. The molding sand is made up of is a mixture of silica, clay and some moisture. If water is present in the sand, it is known as green sand. And if you remove the water, if you heat that green sand and water or complete water is vaporized, then that sand is known as dry sand. There is a baking sand. Baking sand is made up of used and burnt up sand. A object is known as core. Core is used to make hollow cavities. If you want to make some hollow cavities inside your product, then this core is used, and to support this core we are using this chaplets. So core is made up of that mold material or anything, and this chaplet is supporting the core. Why we need that support? Because core is inside the molten metal. Core यहाँ पे होगा, उसके अंदर that core is completely submerged under the molten metal. So molten metal has very high temperature, so some thermal stresses are there, some mechanical stresses are there. So lot of stresses are acting on the coal, and if it is completely submerged inside the fluid, then a buoyancy force will act. To make this core at one position, to fix this core at one position, we are using this chaplets. So remember one thing, that chaplet is made up of the same material which you are pouring from here, right? जिस metal को आपको casting product चाहिए, उसी metal का chaplets होगा, because at the end of the solidification we cannot remove your chaplets. So chaplet will be the integral part of the casting. So chaplet material must be the same, that is the molten material, right? Next is your chills. Chills is used to increase the cooling rate of casting, right? In the casting, the most important thing is the solidification. How the solidification start, right? Solidification casting के अंदर कैसे हो रहा है, कहाँ से start हो रहा है, what is the rate of solidification? Because on the solidification depends upon your grain size. आपके solidification पे depend करता है grain size, and grain size पे depend करता है आपका properties of the casted product, right? आपका strength कितना होगा, toughness कितना होगा, what is the hardness, what is the ductility, all properties will depend upon the grain size. So grain size will depend upon the solidification time, and so in casting, solidification is the most important thing. So if at some part, you can say, if at some part the solidification time is very less, right, or very more, it takes more time to solidify. But if you want to increase the solidification time at that particular time, at that particular location, so we are using this chills. So chills are used there to increase the solidification time or to increase the cooling rate. Riser. This riser is a reservoir of the molten metal, right? After filling the cavity, that extra molten metal will go to the riser. So riser will act as a reservoir of the molten metal, and it will compensate the shrinkage, because after solidification all metals will shrink, all metal will contract. So to compensate that shrinkage we are using this riser. There is a padding is used. Another term is padding. Padding is the tapering of the thinner section towards your thicker section. This is used to avoid the shrinkage and porosity, because if the section is a thinner section, so that point the cooling rate is very high. So for that we are using that padding, so that a uniform cooling or uniform solidification is there. So it will be there to avoid the shrinkage and some porosity. Now if we talk about the pattern is the replica of your exact product what you want. So on the pattern we are adding some allowances. कुछ allowances add करते हैं pattern के अंदर. क्यों आप allowances add करते हैं? क्योंकि there are lot of you can say shrinkage is there, right? When this pattern is removed, on removing the object from the mold, you need some that you will do some vibration to remove it, right? So all this will depend upon the allowances. So first of all, let us discuss the shrinkage allowance. That we can say that all metals are shrinking except lead or bismuth. Bismuth और lead को छोड़ के बाकी सारे metal shrink करते हैं. So the shrinkage allowance is always added to the linear dimensions, right? If you say if you want a length of 2 meter but you have to add the shrinkage allowance, so we will add a 2.5 meter. Let us say 0.5 meter is the shrinkage allowance. So we are now make the pattern of 2.5 meter length, because if you make the pattern of 2.5 meter length, the mold length is 2.5 meter, but if you pour the liquid metal, then after shrinkage it will come to 2 meter and you need 2 meter. So that's why shrinkage allowance is added. So this is always added to the linear dimensions, both external and internal, right? You have to add the shrinkage allowance. There are 3 types of shrinkage in the casting. One is the liquid shrinkage, one is the solid shrinkage, and one is the solidification shrinkage. What is happening? Let us say we have some molten metal of 1000 degrees Celsius and it is in the liquid state, and let us say that your solidification temperature is, let us say, 400 degrees Celsius. So from 1000 degree to 400 degree, the phase is the liquid phase, but temperature decreases. So because of this, some shrinkage is there, that is known as liquid shrinkage. At 400 degrees Celsius, your liquid starts converting into solid, and solid will be there after rejecting your latent heat of melting. So we can say that at 400 degrees Celsius solid is there. So when liquid at 400 degrees Celsius is converted into solid at 400 degrees Celsius, in that some shrinkage is there, that is known as solidification shrinkage. And from 400 degrees Celsius solid to the room temperature, in that some shrinkage is there, that is known as solid shrinkage. So we can say that the liquid shrinkage and the solidification shrinkage, the liquid and solidification shrinkage will be compensated with the help of this riser. This riser will compensate. After solidify, that solid shrinkage, to compensate this solid shrinkage only, we need this shrinkage allowance. So remember one thing, shrinkage allowance is only there to compensate the solid shrinkage, right, from 400 degrees Celsius solid to the room temperature. For liquid and solidification shrinkage, this riser is there. Riser is used to compensate these two shrinkage, right? There is a metal known as grey cast iron. So grey cast iron has negative shrinkage. Negative shrinkage means upon solidification, the grey cast iron will expand. So you have to subtract the shrinkage allowance in the grey cast iron. Just remember one thing. Next allowance is the draft. In draft is, we are making the vertical faces of the casting into a taper faces. Because if the faces is vertical and if you remove the material like this, so it will damage the wall of the mold. It will be very difficult to remove the metal. If you make it taper, so that removing of the metal or the removing of the object from the mold cavity is very easier. So this draft is avoid the mold damage. Next is your shake allowance. Why shake allowance is there? Suppose you are you make a pattern. आपने एक pattern बनाया, उसके ऊपर आपने molding sand डाला and the mold cavity is ready. When you remove the pattern from the mold, आप जब pattern निकालते हो mold में से, तो because some you will shake that mold pattern to remove this. So because of this shaking, the dimension of the mold will change, will increase. So if the dimension of the mold will increase, let us say you want a 100 units length of a pattern, of a object. So we will take the 99.5 meter length of your 99.5 meter length of the pattern, and because of this shaking, the length of the mold will now be 100 meter. So that's why that shake allowance is a negative allowance. So you have to subtract the shake allowance from the pattern, right? This is for pattern removal. Now there is a property of the molten metal, that is the fluidity. Fluidity is the ability of your molten metal to flow, and this fluidity is directly proportional to the pouring temperature. This is directly proportional to the pouring temperature. If the pouring temperature is high, then the fluidity is high. But if you make the pouring temperature so high that the fluidity is very, very high, so that molten metal will not only fill the cavity of the casted that mold, but it also fill some pores will be there in the mold cavity. Some pores will be there, so it will fill that pores also. So we cannot increase the pouring temperature up to a certain limit. Next is your core, and this core is used to, we already see, core is used to produce the hollow cavity. Very high thermal stresses and mechanical stresses are acting, and buoyancy force is there, and to support this we are using chaplets. Next is the permeability. What is the permeability? That when the molten metal is entered into the mold cavity, because of some reactions, because of some impurities, that we can say that gases will form inside the mold cavity. So we want that these gases will go out of the mold cavity. So that is the property known as permeability. So mold must have high permeability, that it will allow the gas to go out of the mold cavity as soon as possible. So permeability number is calculated with the help of this formula, that is VH upon PAT, where V is the volume of air, that is, it is a standard specimen. Volume of air we are taking 2000 centimeter cube. H is the height of sand specimen of which permeability you want to check, that is equal to 5.08 centimeter. P is the air pressure inside the mold cavity, inside the specimen. A is the cross-sectional area of the sand or the mold, that is 20.268 centimeter square, and T is the time in minutes to escape those air outside the mold cavity or outside the sand specimen. So this is the permeability number. Next is the casting yield. Casting yield is that how much is the actual mass of casting you will get divided by how much extra molten metal you poured. So where the molten metal will go? Why we are pouring the extra molten metal? Because some molten metal will be in the riser, some molten metal will be in this runner, some molten metal will be in this sprue. So after taking out the mold, after taking out the casted product from the mold, we cut this gate, runner, riser. So these total are the waste. So that depend upon your cast yield, that what is the actual mass of casting you get divided by the actual molten metal you poured into the cast or into this mold. There are two types of gate in the casting. One is the top gate, another one is the bottom gate. So top gate means the molten metal, if we can say just this is a mold cavity, that molten metal will be fall from the top, so it will cause a turbulence because it will come in a very high speed and it will cause some turbulence, it will erode this mold, right? यहाँ से वो कुछ erosion करेगा, ऊपर से speed से अगर एक height से आप fluid को आप ऊपर से drop कर रहे हैं, it will cause the turbulence. Dross will be formed because of some impurity, because of this erosion. कुछ यहाँ से erode करेगा तो कुछ यहाँ पे एक ऐसा कुछ एक अलग से shape बनेगा. But this top gate is used only for the ferrous alloys. We are using the top gate only for the ferrous alloys. Next is the bottom gate. Bottom gate means like this, right? Suppose this is the like this. This is the bottom gate. When the fluid is flowing in this direction, and it will fill the mold against the gravity. It will fill the mold against the gravity. So in this there is no mold erosion. Mold erosion will not be there. But in the bottom gate we are having unfavorable temperature gradient. In the top gate you will having favorable temperature gradient, but in the bottom gate you will having unfavorable temperature gradient. And in the bottom gate high pouring time is there. Why high pouring time? That is obvious, because you are working against the gravity, so high pouring time will be there. Next is the gating ratio. Gating ratio is the ratio of area of sprue is to area of runner is to area of gate. This is the gating ratio. Next is the solidification time, to how much time it will take to solidify a casted product or the mold cavity. That is here this rule is there that the solidification time will be equal to K into K is some constant, K into volume of the mold cavity divided by the surface area square. Volume upon surface area square is the into K is the solidification time. If we talk about the cylinder, then the volume of cylinder will be pi r square. What is the surface area of the cylinder will be 2 pi r h plus your two circles at the top and bottom, that is 2 pi r square. Right. So from here you will easily get the molding that solidification time. One is a modulus method. Modulus method is also used to find the solidification time. The modulus is your volume upon surface area. This is known as modulus, and generally we say that the modulus of riser modulus of riser is 1.2 times the modulus of casting. Why we need this? Because we always want that the metal in the riser will solidify after the solidification done in the cavity, right? Because अगर यहाँ पे आपका पहले solidify हो जाएगा, then there is no use of riser, right? Because this riser has to compensate for this liquid and solidification shrinkage. So the metal here will have to be solidified at the end. First metal will solidify here, then at the riser. So that's why we can say that modulus of riser will be approximately 1.2 times the modulus of your casting.